So we were talking about the convolutional neural networks, and I just brought back this figure, which was the VGG16 model, and was wondering if you remember what are the components here. So what do we have here? We have our input image, and then the input image is 224 times 224 times 3. What is 3? Number of channels. So you have RGB image, red, green, blue, different channels. And then 224 times 224 is the number of pixels per map, right? Then we do convolution here, and you remember what was the convolution, right? So here it says that you do convolution with 3x3 filter. So what does it mean? It means that the filter is a tensor. What is the dimension of that tensor? 3 by 3 by 3 again, right? So the number of channels should match the number of channels at the input, right? How many of those filters we have in this convolutional layer? 64 of them, right? Because we are computing 64 maps at the output. Great. So you remember that. Now we do convolution, and then we do max pooling. And here in the max pooling, we get from 224 times 224 times 64 into 112 times 112 times 64. I mean, obviously, the number of channels did not change. But what is the stride of this max pooling? It's 2. Great. Yeah, because we are just making the dimension half, correct? Great. So we do that, and again, we repeat this, we keep on going till we get here. Yeah? And this is where we do the flattening. So you remember what we do in the flattening, right? So we have here 7 times 512, 512 tensor, which means that we have 512 different maps, each of them of size 7 by 7, right? And now, then after flattening, we get this number. What is this number? This is exactly 7 times 512. So we get all of those numbers in these maps. We put them in form of a vector, and then we give it to multiple dense or fully connected layers till we get the output. And at the very output, we have 1,000 outputs. Why we have 1,000 outputs? It's the number of classes we have, exactly. So it was ImageNet classification. It has 1,000 classes. So we are going to have 1,000 outputs, each of them giving the probability of the input, the image, belonging to one of those classes. Great. So good that we could remember everything. So we talked about this, and then we get into the problem of training. So this was where we stopped before last week. So we got into the problem of training, and the question that we had was that how we can train these convolutional neural networks. Now, of course, we are going to use backpropagation again, because this is the only thing right now working with deep neural networks. So what was the main idea? This is, again, the classical training problem. So just to recap, we have a bunch of inputs, and I'm showing it with capital X right now, because the input could, in general, be a tensor. It could be image, right? And the image could have 3 different channels, right? So it's a bunch of inputs, which are in general tensors, and then at the output we have a bunch of outputs. For example, they could be classes if it's a classification problem, or it could be a vector, matrix, anything of numbers, right, if it is regression. We have a bunch of things like this. So the inputs, the labels, and then we have B of them, and then we are just going to minimize this average loss or empirical risk. So basically, we compute the loss between theta, and theta is basically the output of our convolutional neural network. So we get every single input tensor, we give it to our neural network. At the output, we see theta. Then we compute the difference between theta and the true label that we have in the data set. We average it over the batch of data that we have, and we try to minimize it. And if we want to do it, we basically just do gradient descent, right? And then to do the gradient descent, we need to be able to compute the gradients. And of course, this means, in neural network terminology, it means that we should be able to just go forward and backward on the network. OK, So we talked about the forward propagation. That's something, I mean, I'm not going to go over it once again, but just briefly to recap, I mean, it's basically what we just tried in that particular diagram of VGG16, right? We start with the input, some channels of maps, like image, for example, and then we pass it through different convolutional layers, activations, anything, till we get to the very output theta, and then we can compute the loss. So the forward propagation is quite straightforward. Everybody can do it, right? So nothing to discuss. Then the next thing is that how we can do backward propagation. And when we want to just do backward pass, we start from the very output, very loss, and then we start computing the gradients, right? So the first thing that we are going to compute is the gradient of the loss we have computed with respect to the output of the neural network, which we can always do it. You agree? Why we can always do it? Because we can take the derivative of loss function. Great. So we compute the derivative of the loss function. We can compute this derivative, and then we could go back over our feed-forward neural network completely again, like what we used to do in chapter 2, correct? So the feed-forward neural network is either a fully connected layer or a kind of activation, right? So all of them, we do know how to backpropagate over them. So we are going to do the backpropagation up to the point when we have this y hat L. And this y hat L is actually the one which we got after flattening, right? So when we started with the very input, we did convolutions, max pooling, whatever, and then we get into one point where we wanted to give it to a fully connected neural network, correct? And at that point, we did the flattening. We got all of those numbers, we put them in form of a vector, correct? So we can get backward, we can do the backward pass up to this point. And then the whole thing is that we want to get backward from this point to the very input. So when I get here, we talked about this. We can simply reform everything in the form of the map that we ended up with, or the tensor we ended up with, right? So we talked about this, that, for example, if I have 3 different maps at the very output, like at the last convolutional layer, and each of them is, for example, say of size 4, then the thing that I can do is that I can get, I mean, I have 4 numbers in this map, 4 numbers in this map, and 4 numbers in this map, meaning that I have 24 different numbers. And my y hat L is going to be 24 numbers, correct? Yeah? So it's going to be y1 till y24. And if I do now how I started, like y1 was here, y2 was here, y3 was here, y4 was here, then I put y1 here, y2 here, y3 here, y4 here. And then I go for the next, sorry, not 24, 12. Come on. So why didn't tell me? I did it on purpose because I wanted to see if you can detect it. But no. Yeah. Okay, so yeah. So 12 different guys. I'm going to put them one by one here. If I do know how I have sorted them out here, when I am computing gradient, when I'm coming backward, I get to this point where I do compute the gradient of r hat with respect to this particular y, correct? And this means that here now, instead of y1 itself, I'm going to have the derivative of r hat with respect to y1. The next one is the derivative of r hat with respect to y2, and so on till the last one, right? And if I do know this vector, then I'm going to get this guy, and I put it exactly the place that I took in my forward pass, correct? So I can put this guy, this particular guy, in the form of a tensor, and then I'm going to call it the gradient of r hat with respect to that tensor. This is the gradient that we are going to start with at the output of our convolutional layers, right? And then what we want to do, we want to just get backward over all of these layers. And the main things that we need to know is that how we go backward through pooling and convolutional layers, correct? Now, do you remember how we did it on pooling? So we need to just, reverse whatever we did in the forward pass, right? So let me just take the mean pooling because that one was the easier one. Yeah, this was the mean pooling. So when we want to do mean pooling, how we do it, we're going to just say, for example, I have this 3x3 input, and then I'm computing 2x2 map. So the convolution going to get this filter of size 2x2, then it's going to just slide it over the input and then writes the average at the output, correct? And then when you want to just go backward, this simply means that you basically have your gradient. But why I don't show? OK, I don't have this here. So you basically do know your gradient with respect to y hat here. So you do know what is the gradient of your loss with respect with that y hat at the output. Yeah. And then, or this is actually a tensor, so I'm going to write it down as y hat. But what we want to compute, we do know this, but we want to compute the gradient of r hat with respect to y, which is the input. And what we do, we are going to use the chain rule, correct? So the chain rule, if I want to use it, I'm going to start with y1, for example. So if I want to write down the chain rule for the y1, what should I say? I would say, OK, the derivative of r hat with respect, of course, if I look at my forward pass, I have y1 till y9, and all of them are going to generate the whole y hat for me, right? So what I can say everybody in this guy, y hat, is a function of y1, y2 till y9, yeah, in general, correct? And then if I want to compute the derivative with respect to y1, the chain rule is going to tell me that the derivative of r hat with respect to y1, this guy is going to be the derivative of r hat with respect to every function of it times the derivative of that function with respect to y1. So it's going to be the derivative of r hat with respect to y hat 1 times the derivative of y hat 1 with respect to y1. And then you can keep on going like this. So you keep on going till the very last one. So the gradient of r hat with respect to y hat 4 times the derivative of y hat 4 with respect to y1, correct? And then you can write it down in form of this summation. But of course, if I am only looking at y1, the thing that is obvious is that y1 is only going to show up in y hat 1, correct? For y hat 2, y hat 3, y hat 4, y1 is not included, correct? And then the gradient here, when you compute this gradient, you're going to have only one term. And then the derivative of y hat 1 with respect to y1 is simply 1 by 4, because y hat 1 was the average of y1, y2, y4, y5, correct? So you remember that, correct? Now, if we write down for everybody, it's going to look like this. And at the end of the day, what we said that we can think of this filter here, or whatever we use for pooling, this filter for averaging in the pooling, we can just think of this guy to be just multiplied to that output map, which includes the gradients or the derivatives. And then we're again sliding over the input. Each time like here, I multiply this filter into that guy, the green map, and then I copy it there. Next, when I go for the next slide, I'm going to again do the same thing, and I copy it there, and whatever is there, I'm going to sum it up with what I am adding, right? But the cool thing about this operation was that we could just give a better intuition or better representation. And the better representation was that we could, instead of doing that reverse form of convolution, we could actually write it down in form of a convolution, right? So you simply need to just get your output. You just do the zero padding so that the dimension is going to match. And then after that, you're going to simply just convolve your filter with that output gradient. And whatever you get there is going to be exactly the ones you computed by the chain rule. So this is the last slide we had it. And that was the moral of the story, that if you are backpropagating over a pooling layer, then you are pretty much doing a convolution. Yeah? You just need to modify your output gradient map. Okay, everybody clear? Any questions? No question? Good. So if you got no question, then let's go for the convolutional layer. Yeah? So we want to see how we can backpropagate over a convolutional layer. And one thing that I should make clear right now, because I'm going to do it in a bit of detail, but I don't want you to just lose the big picture. One thing is that the convolutional layer for us is going to have one tensor as the input. So say this is the convolutional layer. Yeah? So this is a convolutional layer. And this is going to have one input, correct? And this input is what in general? It's a tensor, right? Meaning that I could have one map, second map, third map, and so on, right? So in general, I could have C different maps at the input, correct? This is the thing that I'm giving to this convolutional layer. And now, at the output of this guy, I am going to get one other tensor, right? And this tensor is, in general, of different dimension, right? So it could be now k different channels. And what is this k? The number of filters you have in your convolutional layer, right? So here you have W1, W2, and so on till Wk. And every single of these W's has how many channels? C channels, right? C channels that you have here. Great. And after that, what you're going to do activation, correct? So for example, you put the ReLU function here, and then you are going to get your output, which is again the same thing. I mean, it is going to be of depth k, correct? Now, let's call this guy x. Let's call this guy z. And let's call this guy y. Okay? Clear? Now, when I am coming backward, do we have any other color? No. Unfortunately, no. No? Okay. No. So when we are going backward, so I am going to have gradient of r hat with respect to y. What is the dimension of this guy? What is it? Come on, after reading week, the first session, you should be very fresh. After the second session, you should be again tired. So what is it? What is the dimension of this guy? Is it different from this one? No. It's exactly, same thing as this one. Instead of every single entry y, is now the partial derivative with respect to that y, correct? So this guy is again exactly of the same dimension, right? And then you want to get back. First you pass backward through the activation. Then you're going to get the gradient of r hat with respect to z. And what is the dimension of this one? It's again of the same dimension as z, correct? So it's going to have depth k, same map size, right? And then again from this one, you're going backward here, and then you compute the gradient of r hat with respect to x. And what is the dimension of this one? It's going to be c times the size of every map, correct? Right? So I am starting with one tensor, I'm getting back to a same dimension tensor, and then from this one to this one, I'm changing dimension, correct? So I need to find operations which do these stuff for me. Clear what we are going to do? Yep. Great. So first thing, if I want to just backpropagate over the activation, this guy, should I do anything specific? No? How can I do this? Do you remember? Element-wise product, yeah? So you just do have ReLU. I mean, every single element here is just passed through ReLU, correct? So you are going to compute the derivative of ReLU and multiply it with that gradient here, yeah? So if you have y being computed as f, any activation of z, then when you want to go backward, the gradient of your r hat, the loss with respect to z, is going to be the gradient that you have at the output, the gradient with respect to y, entry-wise product with the f dot of z. And this product is going to work because z and gradient of r hat with respect to y, both of them are of the same dimension, right? So no problem, you can simply go backward. So this is exactly the same thing as what we had in the fully connected, nothing new. Now, the next thing is the linear convolution operation. And once again, what I want to do, I want to get started from this k-channel gradient at the output, end up with a c-channel gradient at the input. But this is very hard that I do it in one shot, so this is why I break it down into multiple cases. First case, assume that the input and output, so the input tensor and output tensor have depth 1. Okay? So we are now having just input map, output map. Clear? Simple case. Now, if I do that, then this convolution is going to look like this. So say, for example, I have this 3x3 input map, and then I convolve it with this 2x2 filter. So I simply slide it over that input and then write down the output, correct? And if, for example, I'm computing this Z4, what I'm going to do, I'm going to multiply these 4 weights into that part of the input, and then I sum them up. I write it down as Z4. Now, if I want to, now what I do have right now, I do have the gradient of r hat with respect to z. So I have this guy, correct? And what I want to compute, I do have, of course, I do have my weight map. The thing that I want to compute is the gradient with respect to input map, correct? Now, how can I do it? I should write down chain rule, correct? So let's just write down chain rule for the first guy, okay, or x1. If I want to just write down chain rule for x1, it means that I want to compute the partial derivative of r hat with respect to x1. So how can I use what I have here at the output, that gradient with respect to z, in order to compute that one? Any idea? Exactly. So basic chain rule again. So the thing that you are going to do is going to say, okay, I want to compute with respect to x1, so I'm going to start with every single guy that I have at the output, because the whole green map is a function of x1, potentially. I mean, it could be that x1 is not showing up in one of the terms, but it doesn't matter, because chain rule is going to just make it 0 at the end. So I'm going to write down the partial derivative of my loss with respect to z1 times the partial derivative of z1 with respect to x1. Then I go for z2, so I'm going to write it down, partial derivative of r hat with respect to z2 times the partial derivative of z2 with respect to x1. And I keep on going till z4, correct? So this is going to be the chain rule. Now, let's do it. So let's write down, this is the chain rule that I wrote here. So partial derivative of r hat with respect to every single z in the output map, and then the partial derivative of that z in the output map with respect to x1. But if you look at this guy, what do you think about those partial derivatives of z with respect to x1? Does it show up here? Yeah. What is that partial derivative? Exactly. It's going to be W1 because you have this Z1. Z1 is basically W1 times X1, W times X2, W3 times X4, W4 times X5, right? And then sum of them. So when you compute the partial derivative, it's going to be W1, right? What about this one? Does it show up here for Z2? No, because Z2 does not have any term, including x1. So the partial derivative of z2 with respect to x1 is going to be 0. What about this guy? This guy? So that makes now sense to you why I have written here w1 times partial derivative of r hat with respect to z1. Correct? Now, what about the next one, x2? I mean, you can do the same thing. Only thing different here is that instead of x1, you're going to write x2, right? And then when you do that, again, you're going to always, you can look at this map. I mean, here, z1 includes x2, and the partial derivative is going to be, what is the partial derivative? It's w2, because w2 is the one which is going to get multiplied with x2. What about this one here? It's w1. It exists. What about this one? 0. 0, right? And then you're going to see this guy, right? So you can keep writing down. And again, like the pooling one, which guy has the most terms showing up? x5, the one in the center, right? Because it shows up here, shows up here, shows up here, shows up here, right? It's always there. So if you keep writing it down, you're going to see, I mean, this is basically what we did. You can do it for every single x from x1 to x9. And you're going to see x5 is the one which has the most one. Those on the edges going to have only one term. Those which are sharing, like on the main half, they are going to have 2 terms, right? So now, if I want to again visualize it, one way is again to think of it as a kind of reverse convolution, meaning that I start with these weights, I multiply them with that guy, and then I just, after doing that, I just write everything down on that window. And then I just shift the window. Again, I do the multiplication, I put it there, and I keep on doing this, okay? And whenever I get into a cell with something inside it, I sum it up with what I have there, right? But given what we saw in pooling, you can guess that this one is again going to show up as a convolution, right? So you're right. You can write it down as a convolution. So you can get your output gradient, and then you get one filter. You convolve it with that output gradient, right? But now, for that filter, this red filter, what do you think it should be? Just let's, for example, consider this guy. First, let's consider x1. So if I want to compute x1, then I should get at my output w1 times this gradient component, right? Now, if I do that, let's look at it here. Okay, then what should be this guy here? It should be w1, right? So what we had initially was w1, w2, w3, w4. But now what I see here is that w1 should show up here, right? Do you have any idea about the other guys? For example, what should be here? It should be w2, right? But how we can say it, we could say it again by comparing this term, right? So we see that w2 gets multiplied with z1, w1 with gradient with respect to z2, when we are computing the gradient with respect to x2, right? Meaning that when I get into this map in the time that I'm convolving, when I just push it one further, then this guy should be w1 as it is, and this guy should be w2, right? So this guy should be w2. And then you can just keep on doing this, and at the end of the day, you're going to see that this is the same filter as you had, just reverse, up, down, left, right. Okay? Clear? And then you can keep on going over all of these, gradient components, and you see that this is exactly what you computed by the chain rule. Everybody's clear? So you got the idea? You get the filter, you just modify it in that form, up, down, left, right. Then you have a new filter, you convolve it with your output, and then you're going to get your gradient with respect to the input, right? So we are still here. We are here. We are just talking about one map thing. So the depth at the input and output, both of them are 1. And then when I want to just get backward, I don't really need to do anything specific. I get this guy. I'm going to convolve it with the reverse version of this filter. And then I end up here. Correct? Now, one thing that you might ask me is that, so this is the moral of the story. So just get your output gradient, and then you just convolve it with the reverse version of your filter. And then we can even write it down in a more mathematical form. So say Z is your output here. And we are still talking about, one map tensor, just a single channel tensor. And say this Z is a map output. This is the convolution of map X with filter W. And then if I want, and I do know what is the gradient of R hat or any function with respect to that Z, if I want to compute the gradient of that function with respect to X, the only thing that I need to do is to just write it down again in the form of convolution, but instead of X, now I put the gradient with respect to Z. Instead of my filter W, I'm going to put this W hat inverse, right? And this W hat inverse is simply the reverse version. The same thing we did on the board, right? Clear? Great. So now, one thing that you might ask me is that, okay, this map could be of some dimension. For example, in the simple example we had here, it was 3 by 3, right? And then at the output, I had some other map which was 2 by 2, right? How can I make sure that when I am doing like reverse convolution, I'm doing this convolution, I'm getting back to the right dimension? So how could it be a problem with the dimension? What kind of things in the convolution could make the dimension of input and output different? So one of them is a stride, right? If I do convolution with a stride more than 1, then this guy is going to have significantly smaller number of parameters, right? So the map is going to shrink. But I'm not going to do it right now because why? So you remember that if I'm doing any convolution with the stride, for example, 2, it simply means that I do this convolution and then I put something after it. What was it? Downsampling operation, right? So I can do downsampling operation after stride 1, yeah? So for the moment, don't confuse yourself. Assume that I'm doing with the stride 1, okay? That's fine. I'm going to talk about the stride different than 1 later. The other thing that is that I might have, even in the example we had, it was 3 by 3, we ended up 2 by 2, right? Now, if I want to convolve one filter 2 by 2 by a map of 2 by 2 and end up with 3 by 3, how can I do it? We did it in the example. Zero padding, right? So as long as the stride is 1 and you do proper zero padding, you're always going to end up with the right dimension, right? So if it is just a problem you want to implement, you look at the dimension at the input, you look at the dimension at the output. Assuming that this stride is 1, you always can do zero padding to fix it, okay? So that thing is not going to happen because you always can do zero padding as we did in the example. Now, of course, I need to extend this further, meaning that I just assume that I have multi-channel output and multi-channel input. But before that, let's just do something easier now. Say I compute the gradient with respect to Z. I get from gradient with respect to Z into gradient with respect to X. What kind of gradients at the very end I want to have? The gradients with respect to weights, correct? So at the end of the day, when I want to just do one step of gradient descent, I'm going to apply it on the gradient with respect to weights, correct? So don't miss that point. All of these gradient with respect to Z, X, Y, whatever it is, we're computing them because they are going to help us compute the gradient with respect to weights. We need that, correct? Because at the end of the day, that R hat, this R hat here, is a function of weights, and you're going to look for the optimal weights, right? So now I started from this point. I have this gradient, I have this gradient, I have this gradient. I also do have x, z, y, because before I start backward pass, I did the forward pass. So everything is here. The last thing I need to compute is the gradient with respect to the weights inside the convolutional layer. Correct? Clear? So let's just take a look and see how can I do it, and then let's get back to the simple example that we had. So basically I have this convolutional layer again, the same thing as I had before. Now what I'm going to assume, I assume that I have this gradient at the output, the gradient with respect to the output map. I do have the input tensor. You can think that I have the gradient also, but it doesn't show up in this in this particular computation. And the thing that I want to compute is the gradient with respect to the weights, correct? So I want to know what is the gradient with respect to the weight. Now, how can I do it? A $1 billion question. How can I do it? Chain rule, right? So always chain rule, nothing else. So I'm going to do the chain rule. So let's do the chain rule again. So what is the gradient with the partial derivative with respect to W1? If I want to do that, what should I write? Any idea? I want to compute the partial derivative of r hat with respect to W1. What do I have here in this map? I do have the partial derivatives with respect to every single z, right? And those z are all functions of the weights, correct? Including weight W1. So what should I do? I simply get this guy. I mean, I start with the gradients with derivatives with respect to z. And each time I compute one of them, I multiply it with the derivative of that z with respect to W1. And then I sum them up. This is the chain rule, right? So I'm going to write it down. The partial derivative of r hat with respect to z1 times partial derivative of z1 with respect to W1. And I keep on going, right? z2, z3, z4, and then it's over, correct? Now, if you do that, if you write it down like this, now, the partial derivative of zi with respect to W1, do we have it always? Yes, this time we have it always, correct? So, for example, look at it here. What is the partial derivative of z1 with respect to W1? x1, great. Yeah? What is the partial derivative of z2 with respect to W1? x2. What about z3? And this guy? x5. Great. So you do have all of them. So it's going to be x1 times the first partial derivative, x2 the other one, x4, x5, right? And you can keep on doing it for every single guy. Clear? So no magic, nothing weird, just the chain rule, right? But this time the cool thing is that everybody has a component. All the components are going to show up because W is involved in all of your computations. Clear? Now again, what can I do here? I could just write it down in the form of that backward or, I don't know, reverse convolution. But again, the cool thing about it is that this guy is again a convolution. So instead, I mean, you just replace your filter with your gradient at the output. So you get this gradient at the output, you put it in the place of the filter, and then you get that filter, which is the gradient, and then you just convolve it with the input. Okay? Then you're going to get the gradient with respect to the weights. Again, you have a convolutional operation. Something simple you can implement. Clear? So, moral of the story again, the gradient with respect to filter is simply the convolution of the gradient with respect to the output with the input. So you basically pass the input through one linear convolution whose filter is simply this gradient with respect to z. Everybody's clear? Any questions? Really, you don't have any question? So am I teaching that good? Okay. Okay, I know this is boring, yeah, just computation. But this is how the neural network works, right? So I mean, after this one, we are getting much less of those parts. I mean, we have still chain rule, but much less detail. Okay, yeah, great. So now, this is simply the 2D case. So as I told you, one channel of the input, one channel of the output. But the thing is that how we can extend it to the multi-channel case. The case where I have the input to be as a C-channel input, and then I have at the output K-channel outputs. All right? Okay? How can I do this? So let's just go one step further. So the next thing that I'm going to do is that I am going to consider C-channel input, but I assume that I have only one channel at the output. So K is now 1, meaning that I have only one filter here, but my filter has C different channels now, right? So it's not map to map, it's tensor map. Clear? So this is the next thing that I'm going to consider. So now filter W has the same number of channels as the input. And one thing that I want to do is that I want to write down that 3-dimensional convolution or tensor-wise convolution now into the form of summation of those map-wise convolutions. And you look at it and tell me whether you agree with me or not. So how do I do the convolution if I have a multi-channel filter? So if I have multiple channels, so say this is the input, and then I want to get one filter and multiply it. How do I do it? I'm going to put filter exactly here, right? And then I just multiply to that part, right? So this is simply like I convolve this guy into the first map, the second map on the filter into the second map of the input, the last map into the last channel of the filter to the last part of the input, right? So it doesn't matter if I could think of it like 3-dimension, where I go tensor-wise over the whole tensor, or I could say I get every single map of my filter, I convolve it with the corresponding map of my input, then at the very end I sum up everything, right? That's the same thing, correct? So this is why I'm going to write it down in this form, and the main reason, I guess you know, because I do know how to deal with this guy now. I just want to use this fact and then deal with that tensor-wise convolution. But everybody see what I'm writing here? So it's clear for everybody? Right? Great. So if that is clear to you, then I can just visualize it in this form. So if I have C-channel filter, C-channel input, I can simply think that I am getting every channel of the filter. I convolve it with the corresponding channel of the input. And then once I'm done with all of those different channels, then I'm going to sum them up, right? And then it's going to build you the computation graph that you are looking for, right? So what do we have here? We do have here the gradient with respect to z. What we want to compute is the gradient with respect to every single map in the input, right? So what would it be? It's exactly the same thing as we did before, right? Because when I am looking, for example, for the moment, they assume that all of those x's, z, w, everything is a scalar, okay? So if I have x1 times w1 plus x2 times w2 till the last one, and then I sum them up and I get z, then the partial derivative of z with respect to every single of them is the same thing as I just remove everything else, right? So it doesn't impact at all. In other words, if I want to look into one particular channel of the input, I'm going to do exactly the same thing as before. I get my output gradient, and then I just convolve with the corresponding filter reversed. Clear? So everybody got the idea? So that's nothing specific. I mean, this, if I look into one of them, this is exactly the two-dimensional map-wise convolution that we did before, and we do know how to move backward, right? So that is simple. So when I have a tensor input and I have a tensor filter, then but I have a map at the output. If I want to compute the gradient, if I know the gradient with respect to the output map, I'm going to convolve it with the reverse version of every single filter, and then I'm going to get all of those gradients at the input. And when I put them next to each other, it's going to be a tensor of gradients. This is what I want. Yeah? So that is easy. Now, of course, I mean, you can simply write it down in this form. So this is the gradient with respect to the first map, or first map. The next gradient is with respect to the second map, and so on till the last map. And then when you stick them together, concatenate them together, it's going to be the gradient with respect to the whole tensor. Clear? And those W's, again, they are the reverse version. Left to right, up to down, right? Everybody's clear? Great. So now, right now, what I do have, if I have a map here, I am happy because I can get from that map to this map. And then from this map, I can simply get into this tensor. That's fine. Last thing, I just have multiple maps. So I have a channel at a tensor at the output. Okay? So this is the last case where I have a multi-channel convolution, a complete multi-channel convolution. And that is that, okay, this guy, it was simply the, this was simply the diagram of what we had before. So this gradient, you are going to convolve it with every single filter reversed, and then you're going to get the input gradient. So just the reverse action. And the last thing that I want to do is that I want to think about the C channel input, K channel at the output. And when I have K channel at the output, what does it mean? It means that my convolutional layer has K different filters, correct? Each of them C channel, right? Now, so I have W1 to WK. These are the K different filters that I have. Every single filter has C different channels. And again, I can open it up in form of the the kind of convolution I had before. Yeah? So if I think of one particular map here at the output, so for example, the map of the first map, the first channel of the output, Z1. What is it? What is Z1? It's going to be the input convolved with W1, right? So this guy is convolution with W1. Z2 is the convolution of X with W2, correct? And so on till the last guy. This is ZK, capital K, and that is simply the convolution of the whole input with the last filter, correct? So, great. Now, I can just write it down like this. So ZK here is one general channel, right? One channel K at the output, any single of them is simply the input convolved with the corresponding filter. Yeah? Great. So now, how can I show it up? I could say that I have X. This is now input. I'm sorry that I did not reverse it, mirror it, but this was easier when I was making the slides. So X is now input, here is now the output. So this guy is X, the one which you give to your layer. And then you're going to convolve it with K different filters. You're going to get your K different maps at the output, correct? And now, what you want to do, you want to just compute. You do know the gradient with respect to these Z values. The things that you want to do is you want to compute the gradient with respect to this input X, okay? And I should again write down here chain rule, but I don't want to open up those, partial derivatives anymore. This is the moment of truth. So this is the time that I'm going to start cheating in the course. So I'm going to do this kind of cheating from now on, which is not mathematically very concrete unless we could properly define it, but that's fine for us, right? So whenever I say I am computing the gradient of A with respect to B, it means that this is a guy which includes all partial derivatives of every single entry inside A with respect to every single entry inside B. So this A and B could be different things. They could be scalars, they could be vectors, they could be matrices, tensors, anything. And we don't want to complicate the things, so we're going to always show it like that. For example, if A and B, both of them are scalars, what is that gradient? Gradient of a scalar with respect to another scalar, it is the scalar is a derivative, right? Now, if I write down if A is a scalar, B is a vector, then what is that gradient? That is the real gradient that you know it, right? So it's the partial derivative of the function with respect to all parameters. But A and B could be, for example, both of them vectors, right? And this is going to be the Jacobian, and you can extend it to larger cases, right? A and B, both of them tensor, right? So you start from the first entry in the first map of the output tensor, and you compute the partial derivative with respect to all guys inside the input tensor, right? And then you keep on going, so the dimension is going to expand, but you don't really need to think about it. I mean, always think of it like as a scalar, okay? It's not going to change anything. So I'm going to do that, and now if I do that, then I can write down the chain rule much easier. So say z is a function of x, and r hat is a function of z. Now if I want to write down the chain rule, if z and x, everybody is a scalar, what do? I'm going to write down that the partial derivative of r hat with respect to x is simply derivative of r hat with respect to z times derivative of z with respect to x. But now it's a bit difference here, right? Because they could be potentially tensors. And then these guys are going to change dimension, right? And then if you want to multiply them together, you need to know the right product, right? So this is why I use this circle sign here. Okay, so it is a product. And I don't want to know what it is, right? Whenever I need, I'm going to find out. Clear? So then this is still the chain rule, but much easier, right? Everybody's clear? Now, if you got the idea, then let's just look at this diagram once again. So what I do have the gradient with respect to z. So meaning that I do have the gradient with respect of the loss with respect to every single map at the output here. And what I want to compute is the gradient with respect to the input, correct? Now, if I forget about these maps here, so if I just have one single map here, you do know how to move backward, right? We did it before. It was simply a convolution again, right? Now, since I have multiple maps at the output, and all of them are function of x, what should I do? I simply need to use again the chain rule, but I can use it directly on the maps, right? So what I can say the first map is a function, which is f1, is that convolutional layer, or that particular convolution of that particular map. So function of x, z2, the second map, is again a function of x, till the last one, all of them are function of x. And if I want to write down the chain rule, how should I write it down? Let's write it down together. So I want to find the gradient of r hat with respect to x, and I want to write it down with chain rule, but just use the cheating version of me. So how do I do it? It's going to be the gradient of r hat with respect to z1, right? The first map, correct? So here is z1. Clear? Then I'm going to multiply it with what? Please? Gradient of x. Great. Yeah? So what else? Should I keep on going? z2, z3, z4 till zk, right? So it's going to be plus gradient of r hat with respect to z2 times gradient of z2 with respect to x. And you keep on going till the last one. So instead of all of it, I can just write it down summation here. Instead of 1, I write down k. And now k goes from 1 to k. Clear? Everybody got the idea? So it's again the chain rule, but I'm now writing it down in a more general form. Correct? So if I write it down in this form, now gradient of r hat with respect to x is basically sum of those partial derivative with respect to the output maps times the partial derivative of the output map times with respect to x. Now, look at this one particular guy. What is it? If you could tell me that, then I'm sure that you really did not have a question and you got everything. Wow. Yes. Great. Thanks. So everybody got the idea? So I'm very happy. So this is actually the convolution, correct? Because you are looking into one map, right? So I'm talking, when I write down the chain rule, I simply am writing the chain rule over this particular branch. And if I want to get from that map into the input, I do know how to do it. It's just a convolution, right? Great. So this is what we computed for single output map, right? Single map output. Great, right? So what I can say this guy is simply this one. So don't get confused. This is simply the extended version I showed you in the other one. So basically, this is the convolution of every of the output gradient map with every single filter reversed, right? And I put them next to each other and see different channels. Clear? Now, this guy is the first map of this gradient. Once again, just don't miss the big picture. This gradient with respect to x should have how many channels? C different channels, because x has C different channels, right? Correct? Now, this guy is the first channel. This guy is the last channel, the channel C. Correct? Now, I'm summing up these tensors. Can I take that summation inside the tensor? So I have one tensor, I have another tensor, and I'm summing up these two tensors. Okay? This is the same thing as I just sum every single pair of map, right? So instead of writing it in this form, I can write it down in this form, correct? So I could say that the first channel is being summed up over k's, second channel again summed up over k's, and so on till the last one. Clear? Everybody got the idea? Yep. You got a question? No? Great. So if you got the idea, then let's just focus in one particular, this is what we have at the output, and let's focus on one particular channel C. So say I am looking into one particular channel C here in this term. It means that, say C equals by 1. This is simply this summation, right? And what is this summation? Look at it. So I have the gradient of r hat with respect to map K, and then I convolve it with the corresponding filter. So the first channel of filter 1 or filter K, and then I sum them up over all K's. So here is a bit messy, but I can show it more simply here. So if I'm looking into one particular channel at the output, I could simply say that I get the gradient of the r hat with respect to z, and then I go ahead and convolve it with the corresponding filter or corresponding channel of all of the filters, right? So you have filter 1, filter 2 till filter k, and every single of them you just take map number C, and then you convolve it with the corresponding output, right? And then if you sum up all of them, you're going to have map C of the gradient with respect to input. Okay? So I do not expect that you follow all the details, but I hope that this diagram makes it clear for you. Yeah? So what we are doing, we are just, if I want to compute the gradient with respect to map C of the input, the thing that I am going to do, I get the gradient with respect to output, and then I just put the filter, the map C, the channel C of all of my filters, and then I convolve them. Okay? But you don't even need to think that complicated. The thing that you can do is that you can again get these guys. I mean, this is again itself, whole of it, is a three-dimensional or tensor-wise convolution. Because if I define this filter, WC dagger, to be simply channel C of all of those filters that I have. Yeah? So I have k different filters. I go for channel C of every single of them. I reverse all of them, and then I put them inside a k-dimensional tensor, right? This is again a tensor, a filter tensor. And then what I showed you before, that gradient with respect to channel C of x, is simply the convolution of the output tensor with respect to this new filter. Okay? So you got the idea? And since the final gradient is going to be collection of all of these C different things, you can simply write it down in this form. Yeah? So you could say that I had here k different filters, and at the output I have k different channels. What I want to compute at the input is C different channels, right? If I want to again get backward with a convolution, how many filters do I need? C different filters, right? Because your output has C different filters, right? How can I make those filters? It says that just start with the channel 1 in all of these filters and stack them together. It's going to be your W dagger 1. Channel 2 of all of these filters, stack them together. It's going to be W dagger 2. And so on till W dagger C, which are the C different channels of every single filter you have. Clear? And of course, when you put them here, you should do that reversion, right? Up, down, left, right. Clear? So you got the idea? So it's again a convolution, same thing as before. The only thing is that you should play around with this filters, right? Resort them in a form that the dimension matches. That's it. Yeah? Any questions? Ooh. So now questions. So moral of the story, if you want to just do, if you are here really at the output and you have the gradient with respect to z, the only thing that you need to do is to just resort your filters and you convolve this gradient with these filters, you are going to end up with a gradient with respect to input. And of course, you can go ahead and compute the gradient with respect to the weight. So this is the moral of the story. I do know that it's a bit messy, especially in the last case, but I hope that it could just transfer the main idea that whenever you are moving backward on a convolution layer, you basically do a convolution again. You just need to resort your filters, right? Clear? Any question? And when you want to just remember how you should resort them, you should always take a look at the dimensions, right? So now, moral of the story, as I said, is that so if you want to just move completely over a convolutional layer, first thing is the activation. For the activation, you simply do an entry-wise product, and then you get into this gradient with respect to z, and then when you want to again move backward with a linear convolution, you again do a convolution with a resorted filter, right? So that's it. And if you want to compute the gradient with respect to weights, you always need to get your input, and then you convolve it with the gradient of the output. Then it's going to give you the gradient with respect to weights. In the three-dimensional case, it's going to be the same, right? OK, that's it. And we are going to have a very short break, and then we're going to talk about the case with a stride more than one or different than one. OK? OK. So shall we go on? Okay, so the next thing is that, I mean, up to this point, we basically do how to move backward. And we also do know how to move backward through the pooling layer. So we basically do know how to be able to just do the whole backpropagation over a convolutional neural network. The last thing is, however, to know how to deal with a stride different from 1, right? And then if you remember, when we have a stride different than 1, it doesn't matter if it is integer stride or fractional stride, it's always a resampling, right? So we talk about this, that if for example, we are doing convolution with a stride more than 1, or even pooling with a stride more than 1, it simply means that we do the convolution or pooling with stride 1, and then after that we get the output, and then we compute the downsampling, right? So we just downsample with factor 2, for example, if we are doing with a stride 2. Now, the point is that if this is the case, then as I told you initially, this is going to make the life much easier, because now instead of doing the backward pass over a convolutional layer with a stride different from 1, I can simply move backward through the resampling layer, right? So if, for example, I have integer stride, then I could simply say that this convolutional layer with a stride, say, for example, 2, this is equivalent to having a convolutional layer with a stride 1, and then I'm going to give it to 1 downsampling with factor 2, right? And now, if I want to move backward from the output of this guy to the input, I simply need to just move backward from the output of this downsampling to this point. And from this point on, we do know how to move backward, right? So I need to know how to get backward over downsampling. So how can I do this? This is quite, I mean, I guess that you do see it right now very easy. So say I have this input map, which is x1 to x9, and then I want to do downsampling with factor 2. If I do that, then it's going to be the first guy is going to be this one. So z1 is going to be x1. What is going to be z2? It's going to be, what is it? x3, right? So it's going to be x3. What about z3? x7, exactly. And the last one is x9, right? So you're going to get rid of this row and this column, and then this is going to be your output map, correct? Now, what you want to do, you want to just, again, write chain rule, correct? So you do know the gradient with respect to z. Now you want to know the gradient with respect to x. Again, the same thing. I just cleaned it here. OK. Yeah. Again, something like this. So you're going to have the partial derivative of r hat with respect to x1. It's going to be the partial derivative with respect to z1 times partial derivative of z1 with respect to x1, and so on till the very end, correct? So you're going to just write down the chain rule again. So partial derivative of r hat with respect to every single z, and then that z partial derivative with respect to x1. But that one here in downsampling, I mean, if I change x, what it would be? I mean, all of these partial derivatives of z with respect to x1, or any x, is either 1 or 0. Because that z is either exactly that x, or it is not. It's some other x, right? So this is going to be 1 and 0. For example, here, zi with respect to x1, only z1 has a component. Because z1, look at it here, z1 is exactly x1, right? But z2, z3, z4, they have nothing to do with x1, right? So the derivative of them is 0. And what is the partial derivative of z1 with respect to x1? Partial derivative of z1 with respect to x1 is 1, right? Because z1 is exactly x1, correct? So this is why I write down here simply the derivative of r hat with respect to z1, right? So what about derivative with respect to x2? Any idea? It's going to be 0, exactly, because none of those z's is going to include x2, right? So partial derivative of every single z at the output with respect to x2 is 0. So that summation is going to be 0. And you can keep on writing it down for every single guy. Yes, you have?
So since that row, sorry, column and row are going to be zeros, we just can upsample, right?
Upsampling, yeah. It's downsampling, then you do upsampling. Yeah, it's the same thing, exactly. Okay? So if you keep on going, as your friend said, for every point which you have collected in downsampling, it's going to be exactly the corresponding derivative. Any other guy, it's going to be 0. And this is going to look like this. If I put it in the form of the input map, it is going to look like this. So z1, the derivative with respect to z1 is going to show up here. Everybody here is 0. z2 shows up here, z3, z4. And what is this guy? How can I move from green map to the blue map? Upsampling, exactly. So I'm basically doing upsampling with the exact same factor. Clear? So backward pass, if you do downsampling, then you want to move backward, you do upsampling. Clear? So the problem solved. So here I have stride more than 1. Then I'm going to write it down in form of a stride 1, and then downsampling. And if I want to move backward, whatever the gradient here is, I do first upsampling, then I do one convolution with the reverse filter, then I'm going to end up with the gradient with respect to input. Clear? Great. So same thing we can say about upsampling, right? So it could be that I have, for example, convolutional layer with a stride 1/2, right? And we talked about this. This is going to be first an upsampling, so I'm going to do upsampling with factor 2, and after that I'm going to do one convolution with a stride 1, right? And if I want to move backward, again, I do know how to move backward over this convolutional layer with a stride 1. We did it. The next thing is how I can move backward over the upsampling, and you can guess. This is simply downsampling now, right? So say you are doing upsampling with factor 2 here, so x1 is going to show up here, x2 here, x3 here, x4 here, and everything else is going to be 0. So you can write down your z values in terms of x in this form, and again, you need to start doing the chain rule to get into the gradients with respect to x. So you would say, okay, I have the derivative with respect to, for example, I want to compute derivative with respect to x1. So I do have the derivative with respect to all z guys here. So the thing that I can write it down is of this form. So I'm going to start computing those partial derivative with respect to z, which I do have, multiply them with partial derivative of those z's with respect to x1, and then I just sum them up. Which in this case, if you look at, for example, for the case of x1, for example, x1 only shows up here at z1, right? And everybody else, every other z has no x1 in it. So the partial derivative of zi for any I but 1 is going to be 0 with respect to x1. And the only thing that is going to remain is that z1. And the same thing going to happen for every single other guy, right? In other words, when you want to move backward over an upsampling, you simply get these gradients, and then you do the downsampling, you get into the gradients with respect to input. Clear? So again, you do convolution, downsampling, you're back to the input. Everybody's clear? Any questions? Any questions? Perfect. Okay. Great. So moral of the story, resampling, downsampling and upsampling just exchange in the backward pass. So that's going to be it. And that's it. If you have also a combination of that, so if you have, for example, convolution with the stride 3/2, then it's going to be upsampling with stride 2, convolution with a stride 1, and then you have downsampling with a stride 3, and then again you do know how to move backward here. Upsampling, convolution, downsampling. All right? So always you can move backwards. So moral of the story is that forward pass and backward pass are very similar. I mean, they are basically dual of each other in the convolutional neural networks. I mean, this was the case also in the MLP, but in convolutional neural network is more interesting because this kind of give us a very efficient and simple implementation. So if you are going forward pass, I mean, if you are doing forward, I mean, for the last MLP that you have in your convolutional layer, I mean, if you do forward pass there, then you just do the simple backward pass as before. If you do pulling, then you do backward pulling, which is basically a convolution, right? If you are doing convolution, again, the backward is convolution with reverse filter. If you are doing downsampling, there you do upsampling. If you do upsampling, there you do downsampling. So everything can be implemented in the dual form, and this is why we are very, I mean, this CNN was one of the first kind of neural networks which impressed us, because it could just do a very good job, and we could basically implement it very easily. So it was efficient implementation, gradient descent was really working, backpropagation was really working, and this was somehow the rebirth of deep learning was proposed by these convolutional neural networks. Okay? So whatever we talked before in the MLP, we can again do it here. For example, you can do dropout, you can do normalization, input normalization, you can do batch normalization, and you can do data processing here. You might imagine it's going to be much more messy as compared to the MLP. This is why I just did it there, because there it is easier to understand. But conceptually, it's the same thing, right? And the last point is that whatever these guys were doing with MLP, for example, we used dropout in order to get rid of overfitting, right? Again, if we do it in CNN, we are again doing it because we want to get rid of overfitting. The same purpose, the same approach, just, you know, it's going to get a bit more complicated. Clear? Great. So that's it. So up to this point, I was very precise. Now at this point, I just want to give you a final remark, because you probably get out there and I don't want you blame me for teaching you something impractical. So in the literature, or for example in PyTorch, or many people who are practically talking about convolutional neural networks, they call what we do, this tensor-wise convolution, they call it 2D convolution. Why they call it 2D? Because you have your input tensor, then you get your filter, and your filter is going to move in 2 dimensions, right? So you start to go, for example, right, then it comes down, again it goes right, down, and so on, right? It's not going to move in depth, correct? So this is the most famous form of convolution that we have, most practical. People say 2D convolution. And throughout the lecture, sometimes I use this map-to-map convolution as 2D convolution. I mean, to me that makes more sense, but out there, people do not, I mean, they do call this one also 2D convolution, because there exists also 3D and 1D convolution. So 2D is the most popular one, is the one which you always use in practice, but you might get into 1D convolution. So this is what you have in your assignment 3. So it's easier because your input is, the input tensor is not anymore, I mean, you can think of it as a vector, right? And then your filter is again a shorter vector and it's just moving over it, right? This is what some of you had it in signals and system course, right? That was the convolution of the discrete signals, right? That is the same thing, yeah? But there you do it for infinite length filter, right? Here we do it for a finite length filter. It's the same thing. So this is 1D convolution. You could have 3D convolution, meaning that your filter does not need necessarily to have the same number of channels anymore as your input. It could have less channels, right? For example, half channels. And then you start from the top front left, you go to right. When you're over, you don't go down. You just go in depth in, right? And you keep on going till you finish with the depth. Once you are finished, then you come down, you again start from front, left, you go to right, and keep on doing it in depth and so on till you're finished. Clear? So you can do it as well. It has applications, but most things that you are at this stage working with are usually done with 2D, and everything we have done here simply extend to there. So you pretty much learned the most general and most practical one, so it's super easy to extend it to any case. So this is the two-dimensional convolution that we had in the lecture. You could have one-dimensional convolution, start from left, you move to the right, and you could have 3D convolution. So you go also inside depth, yeah? You move in depth. And of course, then your output is going to get a bit more, challenging to be computed. And other forms like depth-wise convolution, things like that, but they are not really important. As I said, the most important one is this two-dimensional convolution, which you use, and all of them you can always write it down as the combination of a bunch of map-to-map convolutions. So that's it. Okay, this is over for chapter 4. And if you do you have any question on chapter 4? One. Any question? So was it clear? So everybody has no feeling about convolutional neural networks? That's great. This is the most important thing you need to have from this course, because CNN is the most serious one, yeah? And then anything else you can always build by your own knowledge, right? And I'm not going to do that messy chain rules anymore, okay? We are going to have chain rules, of course, but they are going to be very easy ones, because I have the cheating notation. Any questions? No question? Everybody's clear? Great. So one thing, if I wanted to just do it conventionally, like if it were a couple of years ago, then at this point I'm going to start with recurrent neural networks. Yeah? But this is the next chapter. I have this very short chapter, which is about skip connection, or what you might have heard of, residual networks, ResNet. This is one of the most serious, CNN-based architectures that nowadays you use for visual tasks. And they are using some particular thing called skip connection, which is not a very new block, but this has some very interesting reason behind it. So we have this particular chapter, which gonna improve, extend our knowledge in CNN, and then after that, we are going to start with RNN, okay? Now, good thing is that for the first part is just a story, so you can relax and listen to the story of CNN or a neural network. So a bit of history about this convolutional neural network. So one of the first serious ones was LeNet, proposed by LeCun in 1998. Yeah? So this idea was that, he was one of the guys, he believed on backpropagation because, just to know, there had been people, probably there are still, but at those days, like the day LeCun was working, there were two kinds of people in this community, or community of computer science. Some of them believed on backpropagation, some of them believed that it doesn't work, right? Simply it doesn't work. Okay, so LeCun was one of them who believed that it works, and he could develop backpropagation for CNN. And the CNN that he implemented, it was quite easy, but quite impressive for his own time. So what he did, he just implemented this neural network, which nowadays you can do it easily as a kind of very simple assignment. But at that time, he just put lots of effort because he had to do all of things we did here from scratch, right? So his model was taking 132 by 32 image as the input, and it was going to do recognition. What is it? A, B, C, D, the letter, what is written inside it, okay? So a kind of, a small class of outputs. And then it was the architecture he used. So he had the convolution pooling, and the 3 layers of fully connected layers, okay, MLP. And then at the output, he just classifies. And it worked, but it was not impressive as compared to, rule-based algorithms at that time. And you might guess why, because the computation was not enough that he could train it very well probably no enough data, no good tuning, lots of things which were not known at that point of time, right? So this was the first thing that he did, but things with neural network did not get that serious at that time. Then there was this particular challenge, which is the ImageNet challenge, started by the project ImageNet in 2010. So in 2010, there was a project called ImageNet. They just collected lots of images. So it was 1.2 million images, and they belonged to 1,000 different labels. Car, airplane, cat, dog, bird, anything, 1,000 different classes, and in total you had 1.2 million images inside this data set. They started a kind of challenge. They said, okay, anyone who can design, at that time they were not talking about necessarily neural network, but any kind of model or any kind of function, algorithm, that gets image and then classifies it properly, then they are going to win that challenge, and it was going on for every year, right? So this was the challenge. So they had this data set. They gave this data set for training. So you go ahead, play with that data set, and come up with your algorithm. And you give us the final model, the final algorithm that you have, and we're going to validate it on the test set. We see the one who gets the least error is going to get the prize, the winning, right? So the first 2 years, 2010, 2011, actually no deep neural network won. Again, because computation plus no proper tuning, lots of things that we do know right now, people didn't know at that time. Okay? So 2 teams got the prize, and they were just using shallow neural networks. Basically, they were doing the conventional, linear logistic classifications, which people try to do, very efficiently with analytic approaches. Yeah? They were doing this. And then in 2012, some people won it, and I guess you know them. AlexNet, right? So 2012 was the team supervision from U of T. Geoffrey Hinton and Alex were the people who won this challenge, and they were the first people using deep neural network for this challenge and winning, right? So this was the point where people call it the rebirth of deep learning, because some people started to believe on the fact that backpropagation over deep neural network going to work, and they can, if we do it properly, we're going to train them properly, train them well. Okay? So this was the first time that they could do it. This is a diagram coming directly from their paper. So they proposed 3 people. It was, I think, a master thesis, and they called it Alex by the first name of the first author, AlexNet. And the network was of this form, which is quite simple. I mean, you can see, but given what you know right now. So you're going to do one convolution, and then you do max pooling, again a convolution, a max pooling, a convolution, a convolution, a convolution. And finally, you do a max pooling, and then you flatten it and pass it through 3 fully connected layers. Yeah? This is something you can do it. The one you do in the assignment 3 is pretty much this one. Okay? So you can simply nowadays implement it, but at that time, without any toolbox, you should write down backpropagation from scratch. And at the same time, you should carry all of this psychological and mental burden that some people tell you backpropagation would never work. So you could even accept that and keep working on that, and then it worked. I mean, this was an impressive work. Yeah? And of course, they took a lot of time to do perfect tuning, I mean, given the resources they had at that time. Yeah? And this was the first, as I told you, deep architecture. It had 5 convolutional layers, 3 fully connected layers. So in total, the depth was 8. Yeah? Only 8 layers. And people started to just believe on this. And some people, for example, Zeiler and Fergus, they worked on the same model. They just did the better hyperparameter tuning at that time, and then they won the next year challenge, so they could do even better than AlexNet. And this kept on going better and better. And at that point, since people started to believe that deep learning is going to work, a very naive and initial conclusion was that deep learning works, backpropagation works, And the deeper we go, the better we get. Because deeper we go, we have more parameters. Because of that, our model is better, more stronger, and it can just learn more complicated functions, meaning that we're getting better and better, right? So this was the conclusion at that point, that we could do better as we go deeper. And this was the point which the next winner, which was VGG architecture by it's the visual geometry group at Oxford University. So they came up with this idea. So they came up with this VGG different architecture. So we saw VGG 16, and they started with VGG 11, 13, 16, and 19. And each of them was deeper than the other one, and they just trained it for this challenge. Trained all of them for the challenge. They won the challenge, in some parts, some tasks, but they had one very interesting observation. And the observation that they saw was that if you start going deeper at the very beginning, you started from AlexNet 8, and then you just go for 11, 13, 16, you're getting better and better. But at some point, when you just jump from 16 to 19, it's not changing that much. Yeah? So you might say, okay, maybe you have very high accuracy at that point, but to be honest, the accuracy wasn't that high, so you still had error. And then the question was, why the slope is just saturating? So what does it mean? If we go very, very deep, we are going to saturate, so is it the final thing? And at that point, many people started to do some theoretical analysis on that. They believe things like they just could rediscover things like universal approximation theorem. So they said, okay, if backpropagation works and universal approximation theory is obviously correct, then it should get better and better. Why it's not getting better, right? So you might say, okay, it's because of numerical things like that, but of course this is not how the science ends, right? So this is the architecture they had. So this is VGG 11. Now you do know what is every single components here. They are simply convolutions and max pooling. And they started to make it deeper and deeper up to VGG 19. And these are the numbers. Oh, okay, the numbers are in the next slide. These are the, not this slide. Okay. But don't I have it here? Okay, that's weird. I thought I have it here. But if you look at the numbers, then this, here, sorry. These are the numbers that we do have. So you look at the error. Here it is 10%, here is 9%, here is 8%, and then from 8.1 you just drop to 8.0. And of course this is not a number you just get with one run. You just take lots of tests. Okay, and you get this conclusion that you get only with 0.1% better accuracy. Yeah? 0.1% is not that much anymore. Yeah? So you expected more. Now, there was also one other winner in the same year, so 2014, because ImageNet started to have multiple tasks. So it was localization, classification, different things. And for the particular, one particular task, this was the inception model that proposed by Google. So it was basically just a bunch of convolutions, and then they just add up the output, combine the output of convolutions, and then again they process it. So it's nothing else but convolution neural network, but instead of just having convolution, they just give to multiple convolution, then they combine it, and they keep on going like this. Okay? And they had less model parameters because they were only using convolutional layers. There was no fully connected layer anymore, except the output layer. And it could be trained faster and less memory, but nothing specific. It was still working same as the other guys. Okay? So now, the point here was that they started to understand was this kind of, there was a kind of stop in terms of depth. And not only they saw stop, when they started to investigate more and more, they saw that there is actually a disadvantage when you go deeper. So what they started to see was that not only the performance is getting saturated when you go deep, but if you increase that depth, at some point you are getting worse even. And if you see something bad, if you say it is worse performance, what do you expect? Given what you have learned up to this point, you might initially say this is overfitting, right? because you get a more complicated model. It has too many parameters, so high capacity. Your data set is limited, so you're getting overfitted model. But that was not the case. So it was shown by Microsoft Research Lab. I think it was 2015. They could show this, that this is not really overfitting. Yeah? And do you look at these two guys and tell me why this is not overfitting?
The errors didn't get larger with the iteration.
Yeah, this could be, but one thing else. Just compare these two. This is test error, this is training error. Training and testing are showing the same trend, right? If it is overfitting, what should you see? You should see when you are doing training, you get better, right? So here, this yellow curve is for 20 layer. When you go for 56 layers, then you should get better in training. Overfitting means that your training works perfect, but when you test, you are doing bad because you have overfitted, right? But this is not really the case. Your training is even getting worse. You see it? So this is not overfitting. Everybody's clear? So this study, I mean, this basically just went through all of those computations to do 56 layers backpropagation to understand what is really happening. Is it overfitting or not? And the conclusion was obviously this is not, because this guy even in training is showing worse performance. So comparing these two guys, you simply can see that it is not overfitting, because with overfitting you should get better training, worse test, right? But in this curve, this is not the case. So here is obviously no, I mean the training is worse, the test is worse, so this is obviously not overfitting. And people at this point, I mean, initially some people came back, like, you know, there are always some people that say, you see, backpropagation is not working. Finally, it shows up, right? But people started to blame, I mean, those who were not like that kind of people, they started to blame vanishing gradient issue for this one, which is correct, okay? And what is vanishing gradient? This is the thing that I'm going to talk about on Thursday. But just again to spoil it, when you have a very deep neural network, when you start to backpropagate, so you go to the very end and you start to backpropagate, you are going to just multiply derivatives to derivatives to derivatives, right? And all of those derivatives could be, I mean, potentially going to get very small numbers, right? And those small numbers start to get multiplied to each other. And at some point, when you are at the very beginning layers, those product of small numbers is going to be very, very small, meaning that your gradient is practically zero. So those weights are not going to change. In other words, your model, I mean, those part of your model are just kept fixed for the whole training period. And this is something that stops your model from fitting better into your data, right? And then the idea of a skip connection helped us a lot to get over with this issue. Okay? So these are things that we are going to talk on Thursday. So thanks a lot. Bruce is coming, and Bruce is planning to solve you the exam questions. Okay? So if you're interested on them, you could just take them.